first row, unfortunately, but I will resume regardless. So, the thing, okay, maybe somebody's coming, I hope so. Okay. So,
you should have said that it's relevant for the exam.
Yeah, most likely, most likely. Okay, perfect. Okay, thank you. Okay, so in case you still want to join, basically the notebooks, they don't require a lot of code running. I will just quickly also go through them. But basically, what I will show you is very briefly an example of how our architectures usually look like when we do, when we do so very commonly, for example, in our architectures, when we collect telemetry, we do through time series databases. So for example, a common, let's say, architecture and microservices would be that you have some sort of data sources. So this could be video cameras, etc., that you connect to a buffer. So then generally you would ingest video frames, and then you could connect different microservices to it. So this could be, for example, service containers that connect there, and then they process, for example, video frames. And very generally, if you remember this monitoring phase where we're currently in, this means we have, for example, service containers that continuously process, for example, video frames, and what we want to know is what is the actual state inside these applications. And therefore we can collect, on one hand, let's say, basically information about how the service is actually doing. So this means basically collecting, for example, what are the latencies of the applications, and also on the other hand collect information about the devices. So this means, for example, how much CPU and RAM is allocated to the different services. And this information we collect in a time series database. In our case, this is Prometheus. And for those of you that are interested, actually I put a lot of references, references here, which means that basically this whole environment, we start, for example, through a Docker Compose file, which then spins up all the monitoring infrastructure. So this means it starts a time series database, Grafana, for inspecting these logs. And then what you can configure is, for example, through a Prometheus YAML, you can configure how the metrics are collected from the application. So when you want to monitor an application, you can, for example, define which intervals you collect, or what are the endpoints that it connects to. And the most important thing is also here, if you want to monitor how the application is doing, for example, you have a scaling agent like this one, which can now connect to this time series database and query all the current states that you have there. And very commonly, for example, if you work with Prometheus, you do this through time windows. So you say, for example, what was the average latency in the last 10 seconds? So you make, for example, rolling average over a time frame. And the data eventually that you get is quite simple, because basically it's just tabular data. So this means what you extract applications is, you can say, okay, for example, this application has this much resources, this much data quality, this model size. So this is what we collect in the very first step. So this means we collect basically what information we get from the application. In the second step now, when we go basically to this analyzing, we try to understand the current state of the system and how it was created. And especially this understanding maps very much to what Sharon was saying in terms of you want to create causal models that allow you to also replicate why we came to a certain state. And the way that we do this, for example, is, as you can see in, I'm sorry, it does not preload here, but the way in which we do this kind of understanding is that, for example, we start from metrics that we get from this time series database. So this can be tabular metrics, like the ones that you see here. So you know, for example, what was the latency at a certain time, what was, for example, also the resources that are allocated into it. And then, together with some variable relations, I can try to build some functions allow me to interpret the model, which is basically a generative model, as Sharon mentioned a couple of times, because such a generative model allows you to understand why certain observations in a system were created. And in particular, these variable relations, it's very interesting how you end up with them, because generally, very frequently, you already have some prior understanding. Because you say, for example, okay, you're an expert, therefore you have expert knowledge, and you say, for example, I know how my system behaves, but this approach is not very dynamic, because usually if you have, let's say, a lot of metrics, and systems can also change over time, or you have just an infinite amount of metrics. Therefore, a very interesting approach is, for example, as we do it here, is that we just take, for example, a couple of these metrics, so we filter the rows that we're actually interested in, and then we pass it to a causal discovery mechanism. In this case, it's a PC, and for example, surprise, surprise, when we try to fit such a causal structure over this data, what it actually tells us is, okay, the throughput of my application is impacted by the data quality. Okay, so if I give it more or less bigger images that I feed into my services, it will impact the throughput, makes sense. If I give it also more resources, so more CPU cores, it will also improve the throughput, makes sense. So this is just basically an indicator which we can also verify ourselves, and that's very useful, because this kind of developments, they can only be learned from data. So what you saw before, basically these metrics, these table metrics, we can just discover these relations directly from the data. And therefore, it's very robust, because it can also adjust over time. And very generally, what we also do now in the next step is basically we create this sort of regression models, which, if you remember this Cartesian blanket that Sharan showed you before, basically shows that if you adjust the system in a certain direction, it will tell you how it responds. So for example, in this case, what I showed is considering the data that I have, for example, after just 60 observations. So imagine that you have a system, you take an action, and then you observe what happened, and you do this 60 times. So for example, this corresponds to 600 seconds then. You can basically create such a model, which tells you, okay, given that I give, for example, so many cores to my application, or this much data quality that I configured, eventually what I will get is this sort of performance. These sort of models are very powerful, because generally, if you have application configurations, and you have this sort of continuous relations, you can just simply extrapolate. This means that, for example, you know what would be the expected performance if you go over there. You also know what happens somewhere here in the middle. Even though you have not explored it, basically you have a sort of understanding of what will happen there. Generally, what we do not have in these models is a notation of uncertainty. But this is very easily updated, because, for example, this is just a simple regression model. Let's say the more advanced version of this would actually be that we take, for example, as I have it here, it would be a Gaussian process. So Gaussian process is just, let's say, another way in which you can fit a process to the data. For example, what you will see here in these images is basically an understanding of, for example, how your application behaves if you adjust it in a certain way, or just increase the size, for example. But the interesting thing is here that, for example, I know, oops, it opened the other three, yeah. So basically this would be the Gaussian process after 15 observations, this would be after the whole 60 observations. And as you can see, this is for the same service basically. In the beginning, we have, for example, here in this area, lots of uncertainty, because we have not explored, we have not known prior what would happen if, for example, if we give it low quality, if we give it less resources. And as we, for example, let's explore long in our system, we get a more stable understanding of the system and how it will behave, basically. And this is a model that you can just train according to the data. So you have these structural relations. For example, you know which variable impacts which variable. So as we discovered before from the data, we know that the resources and the quality impact the performance. And therefore, we can create sort of models from it, directly from the data. Yes, and this brings me to the third step, which is basically using these sort of models in order to plan and infer what are the best corrective actions for a system. And very generally, And for each of these steps, also that I'm showing here, this is a very abstract cycle. So you can basically implement it with any kind of tools that you want. So if instead of, because for example now, what we will use is a numerical solver in order to solve an optimization problem here. If you don't want to use a numerical solver, but you want to use a genetic algorithm, you want to use mixed integer linear programming, it's your choice, basically. But the thing is that all of these components, or let's say tools that you're using around the circle, you're free to choose. But what I do in my work is I use, for example, now I take these regression models that allow me to interpret what the system is doing and I optimize it. How do I do this? Well, the way in which our, okay, I need to preload it again. Okay, I will start from the bottom here because it's basically what you know already from before. So we have this time series database, you have a scaling agent that can connect, for example, to it. You have this tabular matrix, which you already saw. We have some sort of variable relations. So this is, let's say, directed acyclic graph of how variables in your system behave, which we just learned before. And then you can train regression functions, Gaussian processes, any kind of these sort of models that allow you to interpret what a system is doing. We combine it now with two things. We combine it, for once, with service level objectives, because so far there were no requirements involved. So far we just simply observed the system and analyzed it. So we just simply said, okay, what happened? Why did it happen? Now, all of a sudden, we give our requirements. So we say, okay, yes, for example, I want the throughput to be in a certain range, and for example, the latency is more important to me than the throughput. So you can give not only thresholds, but you can also give weights to this. And these kind of things, it's what you can, for example, here, configure in this SLO config. The next thing is that you can, for example, now also give parameter bounds, that you can say, okay, the maximum way in which I can adjust my parameters, which you then pass all together through a numerical solver, for example, in my case, and then you infer the best possible assignments. And that's it. And this is a very powerful methodology, because for example what it can do is that I say, okay, for example, I have one edge device like my laptop and NVIDIA Jetson, and I can throw a couple of stream processing services there, and I can just put all of them together and infer the best possible global assignment over all of them, which is quite useful because it goes further than just saying, okay, what is the best for each of the individual ones, but it can also give you basically assignments for all of them. So for example, building the global best solution of a system. And in the visual animation that you will see later, I think this will become very clear. But generally now to close the loop is, as soon as you have these parameter assignments, the thing is, what you will do now is you propagate them back to the application, and therefore we will basically go back again to this, which just means, okay, we had the scaling agent. The scaling agent basically makes decisions about how it would like to adjust the system, and we just send now the actions to the services. So basically the agent made a decision on how basically it wants to orchestrate the entire processing landscape, and then it basically just sends actions to all of them. And this is just to close the loop, basically what happened here, because now what we did is that we take these actions and we basically send them back to the actual processing services. So in summary, what this for notebooks very quickly showed is that we start with monitoring, for example, an application through Prometheus, through a common time series database, where you can then capture and also consume the current states across the different processing services. You would then, for example, analyze what is actually happening in the system, and you could do so through regression, Gaussian processes, other kind of models, but essentially this allows you to understand why certain states in your system happen. So for example, you can discover that the model size of your machine learning model, the resources that you give it, the data quality impact your performance, and to what degree. And in the next step, you can then use this to infer basically how you want to adjust the different services, and then also, for example, execute this in your environment. And yeah, very quickly about the notation of exploration. So when you have, for example, a system like the one that I just showed you just now, generally what you want to do is you want to very quickly develop a stable understanding of how the different parameters in your systems behave. So therefore, what you, for example, do in this figure, what you can see is that if you have an agent that just simply randomly explores for a certain period of time, it can very quickly develop a stable understanding of how the system actually behaves. And with this, I will just quickly, you don't have to open the site, but basically on this website, what you will actually find is this demo application, which I will just quickly show to you now. You can also, I mean, the URL is quite short if somebody wants to type it. But in any case, what this shows you is that, for example, the scenario. Oops. That's a little bit buggy. Sorry for that. Okay. So very quickly, what you can see here is, for example, you have an application where you have, for example, I don't know what's happening with the cable. You have this sort of 3 applications that you put on one edge device, basically. So this can be your laptop, it can be an NVIDIA Jetson that you have laying around. And basically, you have these 3 services that you want to optimize running there. And you give it, for example, a couple of requirements. So you say, okay, for example, for this LiDAR processing service, I want 30% of quality. This is like, I give it 30% of weight, and then you can set, for example, certain thresholds. But the thing is, you don't know how to ensure them. So what happens now is that, first of all, you have such a scaling agent, basically, that connects to this environment, and it starts exploring. It starts exploring just, as you can see, there is basically on the top, for example, the output of these services changes, which means, for example, it changes the quality, how it zooms in, it changes how much resources it gives to them. And what you can see on the bottom, the most interesting thing, is actually how with very few iterations, you create such a model that allows you to understand how the environment behaves. So that means, for example, like we just explored maybe 200 seconds of how the service is doing. It's currently still exploring randomly, but I think now it starts basically to exploit. So it starts to now go for the best possible solutions that it knows. And now, for example, every 10 seconds, it takes basically the current state of the application, says, okay, how well are my requirements currently fulfilled? Then it basically consorts its models and says, okay, given my current understanding of the environment, how should I adjust this? And according to these models, it then feeds them to a numerical solver and basically gives you assignments for all of these services. And as you can see, in as little as 30 seconds, 300 seconds, it can basically create a stable understanding of how to ensure the service level objectives on this specific device. If you now move it to another one, basically you could use these models, put it on another device, do some fine-tuning, etc. But this is a very, I think, effective showcase of how very quickly you can just use understanding, create such an understanding. I'm sorry, Okay. Whenever I touch it, it breaks. Okay, I will use the clicker from now. Okay, so the summary of what you just saw is basically that in very, very few iterations, I don't even have to touch it anymore. Let's say, in as few as 30 iterations, you could for example, create such an interpretable model of the environment. So basically, this is a generative model that allows you to understand why certain things occurred in a system. And given that you have very limited resources, for example, in this environment you have 8 CPU cores that you would then automatically distribute between the services. And training these sort of models can be very resource intense, for example, for such a Gaussian process. But for example, if you have, let's say, just a numerical solver at the end, you can very quickly infer potential assignments for the variables. And just also to give you a complementary, let's say, analysis together with this application, is that what we took is, for example, we took a couple of workload patterns. So we said, for example, okay, given that you have very bursty workloads, or you have a certain diurnal workload, where during the day, for example, during traffic hour, you would have face high load. And basically what happens is that we take these patterns, we stress the auto-scaling application, and we compare the application. We compare an application that only has basically one strategy, which can, for example, only adjust the resources. We compare it with an application that can adjust the resources and the data quality. And the third one would be that it can additionally also adjust, let's say, the machine learning model size. So you consistently increase the dimensionality of your solution space. And by going to bigger and bigger solution spaces, basically the application becomes more reactive. Because if you have little resources, what you need to be is a little bit twiddle the available strategies that you have. Okay, to show a little bit how I think we can improve these methodologies is that first of all, what you saw before in this animation was that we just had basically random exploration. So we just tried to improve our understanding of the system by taking random actions in the environment. That's not very efficient. Therefore, one way where we will go is to go to very efficient model exploration. This, for example, is an animation created by my colleague Catherine. She will also present a poster on this. But basically, what we need to do, especially if we have very short-lived services that just spin up, where you very quickly need to improve basically the performance of the service, you need to be very efficient. So you may need to quickly identify what are areas in my model that have, for example, high uncertainty, so that you can quickly improve your understanding there. Another thing that we will most likely improve in our future work is also dynamic instrumentation, which means that, for example, if you assume that you have, I don't know, you have like 10 metrics, 3 actions, this basically defines already the entire action space that your application has, and also the observation space. But the problem is that, especially if you have, let's say, evolving agentic machine learning environments, basically application needs to be dynamic. So during runtime, it must be able, for example, to find and integrate new metrics into the available observation space, or maybe by itself find out that it can adjust a certain parameter in the system and therefore create a new action. So therefore this dynamic instrumentation is definitely one way in which we will go, because it allows you to create evolving applications. Yes, and therefore, what I can quickly tell you is that the motivation for our work was that, in particular, these large-scale computing continuum environments, they pose an infinite amount of optimization problems, because you must optimize the performance here, the resource usage there, etc. And therefore, you need to have explorative behavior that very quickly tries to identify a model that allows you to express why a system behaves in a certain way. And therefore, our solutions in particular is that we model these processing environments commonly through partially observable Markov decision processes, which basically tells you, okay, if what is the probability that I will achieve a certain state if I take this action. So basically, these are the very general methodologies that we use here. The benefit is that we're very stable, because if you have this underlying understanding of, for example, why a certain action was triggered, and you can understand it, because you can, for example, also empirically inspect the model. Because imagine that, for example, you're a software engineer, your manager comes and asks you, yes, why did you increase the resources at time X? And you say, yeah, because my Q table said so. That's not a good way. But if you can, for example, show him such a model, such a regression model, and say yes, because this is the underlying understanding that we have, this creates a lot of explainability. And therefore, it's very useful and also, well, sometimes faster than conventional machine learning approaches like DQN, because they need a lot of iterations in order to be fitted. And yes, for future work, as I saw before, one way is sophisticated exploration schemes, for example, through Gaussian processes and, for example, Bayesian learning. And yes, with this, okay, actually I missed the last slide, but this is the last slide. So therefore, I would very much like to thank you for your attention. If there's there's questions, let's say, that regard either Sharon's part or my part, we're both very, very happy to answer them.
Use the mic. Use the mic. We don't hear.
Yeah. So my question would be like, as we increase the dimensions of our model that predicts the efficient use of the resources or the dimensions. Yeah. So my question would be like, it becomes more and more reactive. What could be a possible scenario that the model acts proactively? Like, do we have some more external signals? Some like, what could be a proactive system look like? Like, what is the idea?
In that regard, I think it's a lot about this potential policy length that you think about. Like, you might know. For example, what is the likelihood that a certain failure can occur from the state that you're currently in? So if you have this sort of POMDP models and you have a longer prediction horizon, that's a big problem generally, because the longer you have a prediction horizon, the more complex it is to infer a policy. But I think that this having long policy horizons and knowing what might be basically, for example, I know that there might be, let's say, negative outcome from the first dimension action that I take. Well, I can already anticipate how I will, let's say, how I will circumvent the drawbacks that come from it. But this I can only do if I have, let's say, very long policy lengths, basically. So that's my take on it, I would say. I hope this answers. Okay. Any other questions to Sharon or to me? Yes, Marco.
My question is to Sharon, actually. So, I think you talked about global observability at the beginning. And when I look at these Markov blankets, they seem to be local. So, I wondered, do you remove global observability? Or is it okay if I know my neighbors, the layers in which I'm deeply with? And that's enough, because that to me would be more in the direction of a complex system. I have local interactions to what's actually going on locally.
You can also say something.
I'm sorry, I was too focused on getting the mic.
Okay. So the conceptually, so the Markov blankets are there. Actually, there is nothing said about the locality of the Markov blankets. So you can look at the nodes, and the nodes can be distributed also on different machines. It's a logical construct, the way actually it could work, right? So no, but what I'm saying is that from the Markov blanket itself, they can be distributed, but for practical reasons.
This actually, for this I would actually point to Nepheli, because what Nepheli is doing is she's creating dynamic Bayesian networks, which also have this notation of temporality, which means that, for example, if you have two machines, when you take one action at a machine one, you know that at some point it will, let's say, propagate to, for example, at T1 you take an action here, and I know that you will be affected at T+1, basically. So you can even have this notation of, let's say, time in this Bayesian networks, and therefore also in Markov blankets, basically. So this can encapsulate it.
Hi, thank you for the excellent joint talk. I have one question again about the blankets. So what we are seeing here are Cartesian blankets, right? Now the world is not necessarily connected in that way. So it's intriguing to think about it as linear spaces or some kind of simple relation like the cost increase with quality, or you would expect some kind of relation between these. But then if you do a reconfiguration and things like that, then actually you might have spots in the whole system which might not be interconnected at all. And this is where I think or hope that actually the Bayesian blankets could really provide an answer to things the quality of service people worked on for decades and actually never came up with a computationally feasible and from the modeling perspective simple way to handle it. And now my question is, why didn't you work with the Bayesian blankets here already, or is this something new you came up with and this is one of your next steps? And how would you relate from your current perspective the semantic expressiveness of those two concepts to each other?
What is a Bayesian blanket that has uncertainty, or what is?
Apart from Sharan's talk, this is the thing where you have the node and you have the relation between the SOOs to each other, and then you have a network between the different SOOs, and you know, I can come from, say, a video conference to the audio conference as kind of a degradation of the whole thing, which might require different resources, and has a completely different set of spectrum of its own of quality, price, and involved resources.
Okay, so for my part, I try to keep it simple. I try to keep it very, very simple. Also, in case of, because you mentioned that relations can be very complex in general. Or in my case, what I assumed is that you have convex functions, because you have, for example, just linear relations, convex functions. This makes it very simple and very responsive. Naturally, it can be bigger, can be, I don't know, polynomial relations, can be some blank spots, but in any case, I think we can capture the sort of relations between them. You're right, this is not, let's say, a big enterprise size application. Especially, I think it's possible to have this deep SLO large scale approach here. The problem is just the overhead, because especially if you try to create this sort of large scale structural graphs, it has a lot of overhead. And we're working, for example, on trying to, for example, find the best points in architecture on where you can train, let's say, a submodel, how you can compose them together. But eventually, the way in which I address it is that you have, for example, a subsystem that tries to interpret, let's say, local, let's say, dynamics, and then you try to compose it and try to find interactions between systems. I think that's the only way in which you can eventually come to this sort of low approach, because especially also connecting to Sharon's motivation, we work in very decentralized environments, and therefore you can't have, let's say, one single point in the environment where you try to create one big graph of how everything works together, because we're decentralized, and therefore we're bound to stick also to the drawbacks of this sort of approach. So basically we'll create multiple decentralized models and try to stitch them together. I hope this sort of went into the right direction. Perfect. We have 6 days or so. Everybody hungry? Yeah. It's 4 minutes short. I mean, I don't have a problem to cut it. Last chance. 3, 2, 1. Okay. Thank you a lot for being here. Frank, you know best. I think at 3 we resume. So that's or Marco. Yeah, at 3 we resume. So there's 3 hours of lunch break. Sorry.
Perfectly fine. This is great. I was just wanted to ask you all to come outside in front of the reception so we can take a picture.